Yes. Yeah, you can talk to the. Hi, Rita. Can you hear us?
Yeah, can you hear me?
We can hear you. So we are ready. So probably you can start now.
Okay, okay, thank you. Yeah, so today I'll be presenting this work that I did with Professor Ruffini and Professor Mitarabi on estimating black hole masses using GeV spin down. So, what I'm doing here is based on the BDHN model, binary driven hypernova model, and to understand it, I'm illustrating it with GRB 2201018. So uh, we the progenitor in this model for GRBs is 10 solar mass carbon oxygen star and then a 1.2 solar mass neutron star. So the orbit the orbiting orbital dynamics induces asymmetries in the oxygen star, and that leads to the fission of the star into a 8.5 solar mass star and a 1.5 solar mass neutron star. And the 8.5 mass star immediately undergoes a supernova. So when the supernova ejecta expands and it reaches the two neutron stars, the neutron stars start accreting. And when the massive neutron star reaches enough critical mass, it collapses into a black hole. So that is the first peak that we see in the gamma ray data. And then later there is the formation of the black hole that produces the ultra relativistic prompt emission. So after this, the black hole undergoes a spin down, which we observe in GeV. So I'm using this spin down data to estimate the mass of the black hole in this model. So I'm considering two cases: the case of 160625b, which is a bright long GRB, and we have GeV data observed by Fermilat. So to get the initial mass, I'm modeling the luminosity as a power law, and using the parameters of the fit, I estimate the energy uh, extracted from the black hole during the spin down emission. And I also perform a correction because what we see is the beamed GeV energy, and we need to find the isotropic energy in order to estimate the mass. So, considering a theta of 60 degree, we estimate the isotropic energy, and then finally with mass conservation, the initial mass would be the sum of the extractable energy plus the irreducible mass. So that mass would be our lower limit of the initial mass, and the irreducible mass is fixed at 2.35 solar masses. So this is the most massive neutron stars that has been yet discovered. So that gives us the lower limit, and finally, uh, the extracted energy is obtained from the energy that we get at any moment t from the data. So in this way, we calculate the extract energy from 100 seconds to 350 seconds in this case, the period of observation, and then we estimate the black hole mass in that period. And using the black hole mass energy formula, we can also estimate the spin evolution. Um, we have the irreducible mass and then the black hole mass from the previous procedure, so we can get the spin evolution for the particular GRB. And I also repeated this procedure for the case of GRB 221009A, which is the ultra long, brightest GRB that we have observed it. And the peculiar features, we also have a TeV emission here, uh, which is which could probably be from spin up of the pulsar. But for the purpose of this presentation, I'll be focusing on the GeV emission and similar modeling to get the initial mass, which was around 2.35836 solar mass, and then the irreducible mass is again fixed by the most massive pulsar. Oh, sorry, I have the wrong plot here. It should be a different plot for 22. Anyway, so then we also calculate the spin parameter A for this case, and the time interval is between around 2000 seconds after the burst to around 25,000 seconds. Since it's an ultra long GRB, we had a very comprehensive GeV observation. And finally, this is the summary of my results. The initial mass is the variation between the initial mass at the time of the beginning of observation in GeV to the mass at the end of GeV observation, and similarly the A parameter at the beginning of the observation and at the end of observation. Um, I'm still trying to do this for the case of 220101A. The issue is that it's not well sampled in time. There's not enough data point for me to do a really good power law fit. So I'm still sorry. One second. So we had
Yeah, thank you for this presentation. Can you hear us?
yes. Just one last point, and I'm done. So this mass estimate is very sensitive to the irreducible mass that we fix. Um, yeah, so that's my summary of the work that I have done so far.
Very good. You did for both 160625B and for 221009. And
Um,
the
sorry, I couldn't hear Professor Ruffini's question.
definition, what you said at the initial 038, what is initial work?
Mm. Sorry, could you repeat the question? I think you're far away from the mic. I
Oh, the
couldn't hear
one
you.
A over M. Okay. And okay, everything okay. On
Mhm.
220101 we have made, but this is perfect. Okay, want to go ahead? Excellent. Excellent. We can complete now the author papers with the with the optical the optical, but the gem is there. And they are practically always the same. It's okay. Sridhar, yes. And we have to put all this together with the other value, and especially 220101. But this is very interesting because they're all very similar, like we expect them. I was just trying to see if there was anything particular. I would not say so, because A over m is larger at 0.38, but so is the mass of the black hole and at the zero emission. It's okay. Very nice.
Okay.
For 220101, you did not try?
I did try for it, but for some reason the mass is increasing, which shouldn't be happening in spin down. And I'm trying to figure out what's the issue. I fixed the data. The data is clean now, but I'm not sure if I'm doing some mistake in fixing the 0 point from which the subtraction is done.
One, I did that.
And what happens?
It is in the paper just now.
It's already. And they are the same? Similar?
Yes, it's the same.
Okay. Taghi has done that one, and
Okay.
we can insert all of them then. It's okay. Perfect.
Can I ask a question?
Yes, absolutely. We are in for this.
Yes. What is the difference between the third column and fifth column? The end of gem emission. Yes.
No. One is at the initial A at the peak, and at the end of the emission. That is at the peak. At initial. It's at the peak. Clear?
Yeah.
Therefore, we have all three of them. Good. Now we have just to work on the text. We have to do that. We have to do that because are you there?
Yeah, I think I disconnected for a moment. Can you repeat again? Sorry.
In with org, the data
Okay.
on the binary neutron star.
Okay.
Okay,
Okay.
publication, and there is a paragraph at the end,
Okay.
which is the way to compute the energy of the UPE. It's very new,
Okay.
very complete.
Okay.
Are you there? And you have to look at. Now, we can take that computation and transfer perfectly well to the rotational energy, the spin-up of the new neutron star. Spin-up of the new neutron star. Namely the one that one year has made in red. And we
Okay.
should just apply this formula written by Orge, and we should be able to obtain the energy going between 10 to the 51 and 10 to the 53. of the rotational energy of the spin up of the new neutron star. Because the treatment is practically the same. Are you there? And this would be fantastic because I would like to obtain that to express how beautiful it is, because this explains the jet energy of a rotating of the spinning up neutron star. Up to now, we have only studied it's a completely beautiful new problem, and should be applied to the jet of, if we obtain that, to the jet of observed by Felix. Namely,
Okay.
it's the first time that we consider a, a, a rotating neutron star by accretion being spinned up. And this object being spinned up creates the jet. And therefore, the formula are precisely the one used in the paper of the by of the UPE. It's valid for all the UPE. It's fantastic. We can apply this for the first time. Usually, we have applied for 20 years, given a neutron star, the way it goes down. This we have done for 20 years, 30 years. Here we are interested, given a neutron star, how if it's spin up by accretion, how it will automatically create a jet. This is totally new.
With an enhancement in the magnetic field, for example?
No, this is the incredible beauty. You have a magnetic field given, okay, and the rotational energy given, okay. Now you assume that this object is spinned up from outside.
Yes, efficiently.
Exactly. And it's the first time that we show that a system which is spinning up automatically leads to a jet. This is totally new.
Yes, because the intensity of the magnetic field also increases.
No, the magnetic field remains the same, but due to the fact that you have J cross B to give an effective charge, the effective charge which is inside increases.
By parallel light effect.
Exactly.
Yes.
And therefore, as it rotates, you build up charges, and these charges reach the critical field and emit plus and minus. Very, very, very beautiful. This, and I cannot imagine that nobody did this before, because this is the general solution of the jet. This just came to me listening to the talk of what is his name, of Felix, because it's fantastic. There is something which has been missing continuously, because we have been traditionally looking at a rotating magnetic field losing energy. But we are seeing here electromagnetic field gaining gaining rotational energy. And then J cos B creates charges larger and larger, and the only way to get rid of that charges is by J. I could not imagine, I was never, it came to me the last 3 or 4 days ago. And this can be checked on Twitter.
This is also related with the former paper with Galileo Xu-Guangqui.
It's the same.
It's the same, but okay.
It applies the same.
Yes.
Namely, you have J and B. But the only point is, I don't know how to explain the beauty. I mean, usually we have been speaking about objects slowing down, but we can have objects spinning up. And if they are spinning up like in a binary, okay, in a binary they are spinning up. And then these forces are swapped here. I don't know if you follow. Like in all the systems that was been looking at. And then suddenly it occurred to me, but why is missing an equation? And the equation missing is J cos B equal Q and Q augmenting, and also reaching the critical field and creating a J. Now we have another very beautiful result in front of you, which is the result that you have looked already about the term. And I think you can enjoy yourself in understanding what is telling us. That if you count the number of terms, the energy is much less. Therefore, the energy of term is a subset of the energy emission. Are you there? When you got to the formula. Okay, we have just to take the formula of because I asked him to put in that formula. It should be immediate. Okay. Did you hear what I was speaking about, Rita?
Yeah, I followed it.
In the speeding up of the pulsar, which gets up in the rotational energy. As far as you know, our friend is yes.
Yes, but
Okay. We will put in time to speak. But we are getting there. Thank you. Thank you very much.
Yeah, yesterday, no?
Did you understand what I said?
Yeah, I was following. So let's thank all of the speakers for today, and we see each other tomorrow morning.
Let's